In this video, we're going to look at how to perform a hypothesis test for quantitative data using SAS. So to start out with, there's a couple files you'll need to have. One is the script that has the SAS code in it. You'll also want to either have the Kentucky data set or the data set for your state to follow along with. In addition to that, you'll want to make sure that you have the code book and then also the set of notes that correspond with this script you'll want to have as well. Alright, so we will go ahead and get started. The first hypothesis test that we're going to look at is the one sample t-test. And so a one sample t-test can answer a question like, at the 5% significance level, is the mean BMI of people living in Kentucky during the year 2020 greater than 25? And so notice here we're going to use the value 25 because anything over 25 suggests overweight or obese. And then again, we're going to be looking at that BMI variable. So let's just take a moment and look at the variable in the code book before we get started in SAS. Right, so here is the variable. So one of the important things to note about this variable is it does have two implied decimal places. So what that means is a BMI of 25 is recorded as 2500. Alright, so let's look at the SAS code. So as always, the very first thing I'm going to do is to read in the data. Looks like our data read in well. Right, so next we can look at the code to perform the t-test. So the very first thing I'm going to do is actually go ahead and make a histogram of the BMI variable. One reason that we need to do this is that we need to check if the distribution is approximately normal. Now, if our sample size is large enough though, and in this case it is, the central limit theorem will take over and we don't actually have to worry about that assumption, but it's always good to visualize your data and to see what's going on. So here we can see that BMI has a very slight right skew, but again, I'm not worried about that because our sample size is very large. Next, to perform the hypothesis test, we're going to use the Proc t-test code. So here I'm going to tell SAS that we're going to use the Kentucky 2020 data. We're going to use an alpha equal to 0.05 and HO 2500. What that is the value under null hypothesis. And here we're using 2500 again because our data has two implied decimal places. And then the variable we're interested in is the BMI5 variable. And then the last piece that I skipped over was the sides. So sides specifies the number of tails or directions for the hypothesis test. So notice here U specifies an upper one-sided test, and so this is where you've got greater than in the null value. And since we're testing to see if BMI is greater than 25, that's why we have sides as U. Alright, so let's run this code. Alright, you're going to get a lot of output, but we really just want to focus on these pieces right here. So first, notice that our sample size is 2,669, therefore the central limit theorem is going to apply. And then our actual t-test values are right here. All right, so if we go back to the notes, here I've copied that output. Notice our p-value is less than 0.0001, therefore it is less than 0.05, and our results are going to be significant. We've got a couple data notes and checking our assumption. So our conclusion here is at the 5% significance level, we have evidence that the mean BMI of people living in Kentucky during the year 2020 is greater than 25. So one thing to notice here is I just say, at the 5% significance level, or you heard me say earlier, these results are significant. We never want to say things like they are very significant or, put some kind of quantifier in before significant. The results are either significant or not significant. All right, let's look at our next hypothesis test. So the next one we're going to look at is the two sample t-test. Now previously in the 14.1 notes, we also looked at the paired t-test. We are going to skip that here because the BRFSS does not have paired data. Alright, so the two sample t-test can help answer questions like, at the 5% significance level, is the mean BMI for people living in Kentucky with good, better health different get rid of that extra word there, than the mean BMI for people living in Kentucky with fair poor health during the year 2020. So again, we're going to use the 2020 BRFSS data to help us. So starting here with the code, the first thing we're going to do is we're going to actually look at that health variable and BMI for different levels of it. So let's first go to our code book. Right. So here is this variable. We actually have seen this one before, but remember that it takes 3 different values, 1, 2, and 9. 1 for good or better health, 2 for fair poor health, and 9 for don't know, not sure, or refused. All right, so running this code. So what we're going to get here is a summary for each of the levels of the health variable. We are interested in 1 and 2. So here is the page for 1. So a couple things to notice here. 1, notice we have a large sample size for the BMI. So we had 2,035 observations for those people that said good, better health. And then also, if we look right here, this is the standard deviation of the BMI for this group. Here, for the fair poor health, we had 627 observations, and here is the standard deviation of the BMI for that group. So one thing to notice is you do have a difference in sample size, but that's perfectly fine. But we do need to consider these standard deviations. And so I kind of have a note here. So when calculating the confidence, when performing the hypothesis test for a difference in mean, so let me change that. You need to decide if the population variances are equal to or not. A general rule is to evaluate this using the sample standard deviations. So if the largest sample standard deviation divided by the smallest is greater than 2, then we want to use unequal variances. That is the same as saying if the larger one is twice as big as the smallest one. So remember here we had a standard deviation of about 675. Here we have a standard deviation of about 840. 840 is not twice 675, so we will be safe to assume equal variances. So next we're going to perform that hypothesis test. So the first thing we need to do is remove the responses from the health variable that were the unknowns or the refusals. And so remember it took values 1, 2, and 9, so we could just remove everything greater than 2. And we've seen this before. And then we're going to use the Proc test again, but notice this time I'm going to add in this line right here. This is going to be the grouping variable. So we're going to group by health, and then the variable we're summarizing is the BMI one. All right, so again we'll get some plots and different outputs. Notice here we've got our histograms again. We could use these these box plots to compare variance as well. Right, but here's the output we're interested in, and in particular we're interested in this box right here. So again, I have copied this over to the notes, and you'll see the piece we're interested in here. So notice the pooled method is the one we use if we're going to assume equal variances, and Satterthwaite is what we're going to use if we assume unequal. So we're assuming equal, and again notice our p-value here is less than 0.0001, so we therefore know it's less than 0.05. So at the 5% significance level, we have evidence that the mean BMI for people living in Kentucky with good, better health is different than the mean BMI for people living in Kentucky with fair, poor health during the year 2020. And notice up here in my data note, I am noting those 2 implied decimal places with BMI, as well as our analysis is going to assume equal standard deviations. Right. Next hypothesis test we're going to look at is the Anova test. So an Anova test can be used to answer a question like, at the 5% significance level, does the mean BMI for people living in Kentucky differ with respect to smokeless tobacco use? So again, going back to SAS, we're going to look at another variable this time. And so let's go to our code book and first look at this variable. Here is our variable, and so this looks at whether or not you use smokeless tobacco. So every day, some days, not at all. And I do want to put a caveat here. I don't necessarily think that this is the best one to compare to BMI, but it was one that had more than 2 categories. So I'm not saying this is necessarily the best comparison to make here. And then the 7s and 9s are for the don't knows, not sures, and the refusals. Alright, so again, we're going to do the same thing we did before using that proc univariate, and we're going to look at the summary of BMI for each of those levels of smokeless tobacco use. Alright, so we make this a little bit bigger. So notice here at the bottom, we have for when smokeless tobacco use is 9, we have 3, 2, and 1. So for this particular data set, there were no 7s. Yours might have a 7 if you're following along with your data set. But some things to look at here is we have the standard deviation and the mean for each of the groups. Again, remember, these are BMI values, so they have those 2 implied decimal places. So really for the group 1, the mean BMI is 30.54. Smokeless tobacco use level 2, we have a mean of about 29.91, and then here's our standard deviation, and then similar for the level 3 for the smokeless tobacco. So just like we did with the not with the parity test, but with the t-test we looked at earlier, we need to remove the don't knows, the not sures, and the refusals, and just have the 3 levels of smokeless tobacco we're interested in. So that's what this line of code is going to do. Very similar to what you've seen before. And now we can perform the Anova test. So notice here, instead of using proc t-test, we're going to use proc Anova. We have the name of our data set. Class is the grouping variable. And then here we need to add in a model statement. And so here what we're saying is BMI is a function of smokeless tobacco use. So we're going to run this. Okay. Now what we have here under means, this is also going to ask us to give the means for each of the smokeless groups. And then these pieces afterwards, these are going to ask for different pairwise tests. Alright, so now let's look at our output. So here we have all the way up here at the top. Here we go. Here's where the output starts. So here we have our Anova table, and remember our Anova table is where we're going to pull the results from our hypothesis test. Here the box plots can help us check our assumptions, and remember we're looking to see if we have evidence of unequal variance between the 3 groups. This variance in group 3 is a little bit larger, but it's not so much larger that I am concerned. All right, and then we have some more information down below. So here, this has been copied over to the Word document, right? And so you'll see that copied over here. Notice here we have our test statistic and our p-value. We have our assumptions notes, and then again at the 5% significance level, we have evidence that the mean BMI for people living in Kentucky differ with respect to smokeless tobacco during the year, and this should say 2020. And that's because again, this should say we do not. Sorry about that. So again, at the 5% significance level, we do not have evidence that the mean BMI for people living in Kentucky differ with respect to smokeless tobacco use during the year 2020. And the reason this time our results are not significant is because our p-value is greater than 0.05 in this case. Now, one thing to note here is if our results were significant, then we could go on to do those pairwise tests. And so looking here in SAS, you can see down at the bottom, here are where you would do the pairwise comparisons, but since our overall result was not significant, we would not move on to do those pairwise comparisons. All right, the last thing we're going to look at is regression. You've actually seen all of this before, so we're going to run these. Now, before we primarily just focused on getting the scatter plot and the line, we didn't focus on these results. And so, for example, let's say we wanted to answer the question, does the simple linear regression model with height as a predictor do a good job at explaining the variability of weight? And further, is there evidence that the slope of the line is non-zero? So again, we've created this scatter plot of height versus weight. Here is the output, and these are the two pieces we want to focus on. Notice that both of these are less than 0.05. So at the 5% significance level, we have enough evidence to conclude that the simple linear regression model with height as a predictor does a good job of explaining the variability of weight. And so that's this piece right here. And then further, there's evidence that the slope of the line is non-zero and there's a linear relationship between height and weight. And it ends up in the case of simple linear regression, these actually both contain the same information. So as always, if you have any questions about the code, if you need any help, please let me know.